Nice turnout. I'd like to welcome everybody to today's Friday Learning Series lecture. Just a reminder that this is the first of two lectures by our guest speaker. The second is going to be on the topic of exceptions, and that's going to be on June 25th, same place, same time. Also want to mention that, so this is the first time that we're doing a live simulcast down to the Bay Area for the A9.com folks. Hello and welcome to all of them. So let me introduce our guest speaker today. Andrei Alexandrescu is a name that should be familiar to most developers. He's a world-class expert in software development in C++. See how in demand he is? So in the C++ community, he's best known for his book called Modern C++ Design. He's also, lest I forget anything, he's a columnist for the C++ Users Journal. He's a former columnist for the C++ Report, and he's much sought after speaker at conferences worldwide. So Amazonians will probably be equally interested in his less known past, which includes the fact that he's a rock band drummer, a classical guitar player, and a former paratrooper in the Romanian military. So currently Andrei is a graduate student in computer science at UW, specializing in programming languages. So without further ado, Andrew, I'll turn it over to you.
Thank you, Andrei. Whenever you hear something like that, basically I wrote that. Okay, so whenever you hear anything like that, it means that the speaker actually wrote it and gave it to the introducer. So, hi everybody. My name is hard to spell, so call me Andrei. And today we're going to talk about applying templates towards getting a lot of software by writing not a lot of code. That's a nice trade-off to have. Before starting, actually, I would like to ask you make some quick polls here. How many of you use C++ as their primary language? Okay. How many of you are familiar with templates? This is going to be hard. Too many people. So that is very good, because this is not an introductory talk to templates. It is a talk about how to use templates at their best to get a lot of good effects. Oops, that's a problem. All right. Today's agenda, we're going to talk about, could people in the back see the actual writing? Yes. So there are 3 seats here. You may want to take them. And there too. So today's agenda consists of an introduction to policy-based design, a concept that I coined without having invented it, but I coined it and I made it popular in this book. But who does not have this book? Hands up. You're going to be happy you raise your hand, because this very copy is going to go to the one person who asks the most interesting question. Okay? So here's the prize. Be interesting. Okay? So going on with the agenda, we're going to talk about a very popular artifact of C++ code, which is like a string. And many of you might be asking yourselves, what's going on with the string thing? Because, everybody's ever written a string, and there could be nothing ever that hasn't been already invented about string. We're going to see how we're going to implement a string that, with only a few hundreds of lines of code, is going to have many implementations in one. What I say by that is the same string with a very few tweaks can encompass very different implementations, very different behaviors, and very different design trade-offs. Okay? I'm going to start about something that I'm sure you're familiar with, something that I call the evil multiplicity of software design. My breath comes in the microphone. Okay. Can you hear me? Okay. So the evil multiplicity means like basically like whenever you have to resolve a problem, a programming problem, it's not that you don't have any solution. Most of the time you have too many. I'm serious. You have too many, and the classical beginner's problem is that they have such a large spectrum of solutions to choose from that they don't know which ones are going to stay good in good shape and evolve nicely with the program, and they don't know which ones are going to rot and not scale and transfer into horrible messes. Are you with me? And it's not that we don't know how to do something, it's that there are so many choices that we don't know which one to choose, right? So because of that, I could say that the design of a software system is a choice of solutions out of a combinatorial solution space. Because as soon as you chose, you said, we're going to do this with like 2 tiers, the highest level, right? We're going to do 2 tiers, 2 servers, 2 computers. After you have decided that, a lot of decisions branch out from that one decision, right? Because, okay, so now we have to have security, we have to have networking, we have to have a lot of things in place, authentication, you name it, impersonation. So because of that, the space of solution is combinatorial by definition. That's what really makes design hard. Because we've all seen like programming geniuses who can crank code real fast and are very smart and can abstract very nicely. But design gurus are the older guys, just turns out. Are the older guys because it takes experience to understand what is going to, it takes a time perspective to understand like which solution is going to lead to the good thing and which solution is going to lead to the bad thing, right? Any questions? Could anyone come with an example of a solution that looks good in the beginning and is bad in the end? Very simple, like as simple as you can. Anyone? Solution that looks good in the beginning and transforms into something bad? Yes. A sequential file. Very good, thank you. That reminds me of a database experience I've had. We've had exactly a sequential file for a database, and we do a rewind and linear search every time record was modified or something. And we delivered a product, and we came back like 3 months later, and I remember the clerk who was working in that database, that sequential file, she just presses enter and then takes a break. And I'm like, what's going on? And she's like, oh, the system has to think. So it's got to think for a minute, and then I understood that it wouldn't scale. I was young and reckless. Okay, so let's see how we can tame this evil multiplicity. I hope you all agree that there is an evil multiplicity out there, because we're going to spend the rest of our time solving it. So I hope you're motivated. So let's think of a do-it-all interface, which means very simple. You design a class, a module, an object, a component that pretty much implements all the functionality you need in one shot. That's the do-it-all interface, right? What are the problems with the do-it-all interface? It's inefficient. It could be inefficient under which conditions? Maybe it's doing threading without having to. Very good point. I have a simpler example. A do-it-all interface has to account for all the states in which the component could be. For example, like invoke, find me this regular expression. It's like a complex, parsing engine, and you pass it a regular expression. And the parsing engine has to account for every state that the parsing engine could be in. Like, maybe it has to reset the stream, or shuffle some buffers, or all that. And because of that, you might waste efficiency. What other problems do you think could be? Yes.
Large file times, having to read in all of this crying that you don't need.
We've met, haven't we?
Yes, sir.
Okay. So yes. Hard to learn. Excellent. So let's first talk about this large compile times. With today's machines, compilation time of compilation is not an issue anymore. True or false? Okay, so I'm glad my sense of humor still works. Okay. So definitely that could be a very big problem. And even more, once you make the slightest change in that do-it-all interface, it's going to ripple through everybody who uses it. By the way, large interface implies many dependents. Much functionality in one spot, everybody likes it. Everybody's going to include that file. Everybody's going to link to it. Everybody's going to compile it and use it, right? Okay, intellectual overhead. That's a very good point. Thank you. So intellectual overhead can be what? Okay, that was unintentional. Intellectual overhead can be like a huge problem because learning, I mean, basically, many people would rather do something that's not very complicated rather than learn how some other idiot did it, right? Some idiots, sorry, to be politically correct here. So I mean, most of the time, I would rather, instead of, I have this API that, does something like, searches one thing through the other. You know what? I'm going to write the for loop, and I'm going to be done with it. Okay? So unless the problem domain is very complicated, you might be compelled to do instead of learning. Because learning the tool is going to be, you're going to know it as well as if you've written it yourself, right? So it does make sense. There is one more subtle issue with the do-it-all interface that I wanted to talk to you about, and that kind of dovetails nicely into my second talk on exceptions. The subtle point is that you'll notice that as you design a very large, you implement a very large interface, you're going to have an insidious source of trouble kicking in, which is it's going to be very hard to make that implementation correct. Now, I'm not talking about sheer bugs. I'm talking about exception safety. If a piece of software must do more than one thing, that may fail, you cannot implement that piece of software correctly. Because it means this. I say, I'm going to have this function that first launch a missile, like an SBM, right? And then, I didn't mean that. So you have to, whenever you have to implement like a very complex interface out of multiple functional points that might fail, you better make sure that you have only one point of failure, which is at the end of the of each piece of functionality. That's called in database terminology, atomicity, right? Transaction semantics, right? So you have to have transaction semantics. Well, with a very smart interface, it's very hard to do any transaction semantics. Put this on the stack someplace and keep it for 2 weeks until we meet again. In the 80s, people liked the multiple inheritance idea a lot. It's a temporary secretary, comes very nicely. Could be an animal too, you plug in the animal and all that stuff. Object-oriented people love animals, right? And employees, right? That's employee animal color point. Color point is another, staple. So the problem with multiple inheritance is that you have very poor mechanics. Like imagine this. I want to create a string that is multi-threaded and it's reference counted, right? You're going to discover before long that the multi-threading aspect and the reference counting aspect, they don't juxtapose, right? Is that the right word? Okay, so they don't just superimpose just like that. You inherit two things and by sheer magic, you get the desired behavior. No, they're going to stitch with each other, right? You're going to have to stitch them together. They can't work just by putting them together, right? So that's a major problem. Second, you have the lack of type information, which means the base classes, right, multi-threadable, whatever, reference counted, etc., they have no idea about what's the type that aggregates them. Did you ever have this problem? Right, when you inherit from some guy, the guy has no idea it's been inherited, so it just sits there. and you gotta have it know somehow. There are techniques for avoiding that based on templates. We're going to talk about that soon. So the next language feature invented to address multiplicity was templates. And they are very good because our techniques are going to use them. And they are going to use multiple inheritance as well. We're going to see soon. But I'm going to do this. So the problem with templates alone is that you cannot specialize structure, only behavior. What do I mean by that? Yes, in the back. The best people are in the back.
When you bring in the different parts that are going into the template, you can switch around the parts, but the interface is still going to be the same because that's the original code.
That's very correct. I didn't mean that, but that's very correct as well. What I meant was a very simple design decision of templates per se, which is when you define a template class, you can say, you know what, this particular function of the template class, I'm going to specialize for for ints. Does that make sense? Okay, whiteboard time. Can everybody read this letter in the back? Oh, thanks. Okay. So when I write a template of class T, I'm going to simplify the syntax somewhat. And I say class X, and I define some class. Later on, say X has like a function void foo, right? And whenever I say, X of int car, widget, midget, whatever, dot foo, it's gonna, instantiate that function. It's gonna use it. Now, at a point, I can say, you know what? Foo for X of integers. Now that's a different business. Okay, we're gonna implement it differently. So I write this. I say void X. X of int double colon foo, and all of a sudden I hooked the behavior of X for ints only. I hooked the behavior of X for ints only and for foo only to do a specific thing that's not in the generic function that was here, that would have been defined here, right? So that would be the body of it, right? Who was aware of this particular feature? Okay. You can. That you can. And any questions about this? This is a nice thing to know, by the way. So commit it to memory. You can specialize part of the behavior of a template class. That's a good thing. Now, how about structure? What if X had a float bar? Right? So it has a member. It turns out there is no way to say, oh, you know what? X of int is going to have a bar that's not a float, is a double. That you cannot. So that's the simple piece of mechanics that I was referring to when I was saying, you can specialize behavior for template classes, but you cannot specialize structure. The structure is fixed. Yes?
You get the type of R underscore from a type that is class capital T. Assuming that you've got a non-basic type.
Thank you. That would be another talk. Okay. So where's Andrei? Okay. Talk to your manager. Yes. So there are ways around it, but with sheer templates, you just cannot. Thank you. Now, within the last 10 minutes, I explained this one line here, right? Now, even specialization of behavior does not scale. So even that nice thing that I just wrote on the whiteboard does not scale nicely, because you cannot partially specialize individual member functions for templates with multiple parameters. I'm not going to go into detail here, but in essence, what happens is if I have more than one here, I can't say things like, oh, for T and for int, okay, say I have class T and class U, right? Are you with me? Okay. Now I can say, oh, for x or x of n int and anything, I'm going to implement it differently. I can't. There are ways around it, but
I thought, is that not partial template?
partial template specialization, we have to specialize the entire shebang.
Okay.
So that's the thing. Partial specialization means I'm taking the whole class and I specialize it partially, right? But I can't take one piece of behavior and specialize it. Thanks. Very good point. Nice hairdo. Okay, so now, even that doesn't scale. So basically, it's like kind of a semi-designed, semi-nicely designed feature that could help us, but not a lot. And there's a lot of burden for the user because, as I'm sure you know, template using templates is often not as easy as it could be. Now, the term coined in the book that the nicest question is going to reward is called policy-based design, and it's all about. So you would like to have a nice complex behavior, but you don't want to have it all in one place, and therefore you're going to do the following. I'm going to assemble a large class with nice behavior, complex, from pieces of behavior, little pieces of behavior that I'm going to stitch together. We're going to see in detail how. So policies are a very, like when we talk a policy, we're going to say, oh, this policy is like, takes care of reference counting, or which is like, it's not doing anything. Right? It's an aspect. It's like a little thing of something more complex. So now let's actually start getting into the meat of things.
So
Yes.
how's the reference count policy different than the reference count sort of flavor? Multiple inheritance and
That's a good question. So the question was, okay, so you just named it policy and you're getting away with it after all the bashing you've done to multiple inheritance, right? That was the question. You said it nicely, right? Okay. So the thing is, as opposed to sheer multiple inheritance, we're going to see like how the reference counting is going to be aware about the class that it implements reference counting for. So, and that's key. That awareness is key. It's not dumb, blind multiple inheritance. We're going to inherit smart. We're going to say, oh, you're going to implement reference counting for this string. We're going to see in a minute. Okay, so strings. Who uses std string? Okay, people there don't like std string. For some reason, that third of the room. Okay. So string, like, anybody who's somebody has heard of it. I hope I'm not offending anyone, right? It's a standard component. They offer, just strings, uniform interface, an implementation you can count on, more or less. And now, why would we care about implementing yet another string? Who's having problems with std string? Okay, we could go home now. Let me tell you this. Yes?
When it comes to case insensitive.
Case insensitive versus case sensitive. Okay, well, we could talk about that. So basically what happens with string is that once you pull any string into your application, you're going to have one design that's good for most, it's got to be good for a spectrum of applications. But it turns out that for your particular needs, it's going to perform very bad. And now you might think, strings, come on, like what's the impact of efficiency? And I just happen to have some experience with doing something like that on a large scale application. I used to work for real networks, and just it's an application that takes like, it took an afternoon to compile while I was there. I think it takes more now. It took an afternoon to compile, so it was a large application. And it was of the player, right? And just taking one string out and putting a specialized, more smart string in increased overall performance by 7%. Just that. I mean, not doing anything in particular, right? So that 7% is good. Size was also down by, forgot, but it was a good amount. So another thing, think of this. Think of an application area where you use a lot strings between like 0 and 6 characters. What's that? What's that? What's the problem domain in which we use strings from 0 to 6 characters a lot? Okay, okay, nobody from the East Coast here. Yes. License plates. Oh, that's a good one. Didn't think of it. Come on. Yes. Stock market. And that comes very nice together, right? In stock market, you gotta process the data very fast. You gotta do the overnight analysis of a lot of stocks that you know. And the stock market people have a lot of money to pay you if you write a good string. That's a good incentive, right? Okay. So. Now, how about multi-threading? Who uses std string in multi-threaded programs? Okay, one lucky person. So what's your experience with that? It doesn't work very well. You know, I have a heartache when I hear like it doesn't work well with multi-threading. It's you know, it means it doesn't work, right? It's not. It can almost work, right? It's not almost pregnant, right? It doesn't work, right? So that's a very big problem. And even if you do have an implementation of std string that happens by sheer luck that you were born with to work with your multi-threaded application, once you switch to GCC, you know, 3.4, the next guy, you can't know precisely whether it's going to work or not. Am I right? Does that make sense? Why is that? Why don't strings work well with multi-threaded programs? Yes. They have global locks. They might. Yeah, so that's a good answer. Yes?
The standard doesn't say anything about
The standard doesn't say anything about threads, so how could it possibly work correctly with something it doesn't acknowledge, right? It makes sense. Yes?
They're also mutable. There's a way to have an immutable string. Like in Java, for example, and then it works across.
Yeah, so the mutability issue, like, right, you could have races at the drop of a hat. But what the answer I was looking for was, anyone, the last minute? Yes? Excellent, thank you. Gonna have a tie next time, so I have more, you know. So, yes, reference counting is a big problem with multi-threading. Why? Now that's an interesting question. Why? Two threads, what's the concept? Reference counting, what's the concept that prevents reference counting from working properly with threads? Hands, yes. That's mechanics still. What's the concept? Reference counting, yes. Yes, reference counting, thank you, is hidden sharing. You can share in multi-threaded programs as long as you're aware of it. You can share, no problem. You have the locks, you have the primitives, you have everything. But reference counting, it says, you say, copy the string for me. Give me a copy. And it says, get a copy, but it's not a copy. It uses sharing underneath without you knowing and without you having any control over it. Okay? Does that make sense? So hidden sharing is the problem, the hidden aspect. It's not the sharing itself. Thank you. Now, we're going to do one first thing. By the way, on my website, if you go to moderncppdesign.com, or if you just search for my name in Google, you're going to find my website. And on my website, there is this string implementation. The first step we're going to do is the following. std string has, I forgot, it has like some hundreds of functions. We're going to decompose string into two little components. First, the core, which is going to contain the most essential functionality. And then the shell that basically builds nice to have functions on top of the core. That's a class. It's a classic layer design, right? What's the advantage? By doing this, we're going to focus on the core, tweaking the core, and then the shell is going to just use the core, and it's going to everything. So basically, we don't have to mess with the shell anymore. We wrote it once, and we're going to use it everywhere, right? Okay, the core we're going to tweak and work on and focus on. But the nice thing is that the core is small, so that's important. Okay, any questions so far? Okay, here's how this new class FlexString looks like. It's going to be a template taking 4 arguments. Don't get scared. First is like class E. E in standard terminology is C, like character type. I don't know why they call it E. It's just E. So it's the character type. Then we have the traits that are required again by the standard. Then we have the allocation, right? The allocator that's going to allocate memory for us. And finally, we're going to have the storage model that the string is going to use. The storage model that our string is going to use. And here's the idea. Here's the idea. This is the core. This guy. Storage is the core. You know that little core? This big fella here, brace, is going to implement the shell. Okay? So focus, this is important. So I want to get this across very clearly. So this flex string is going to open the bracket here and is going to implement a slew of nice to have functions, all using storage. And storage is going to implement a minimalia of like 6 functions, right? And it's going to dictate how our string, how our string's fundamental design decisions are carried on. Okay? All right. Now the nice thing about this is, one day I'm going to pull the storage out and put another storage, and everything's going to work, assuming I implement the storage right. And again, storage is not hard to implement right because it's small. But wait, I mean, this is just the beginning. More fun stuff is going to come. I'm going to wake you up. Okay. Now, how about the storage policy? As I said, it's not that complicated. 4 types and 17 functions. And I'm going to tell you which is the hardest function to write. It's replace. Replace an arbitrary substring from the string with another arbitrary substring that could be aliased and so on. That's a lot of stuff. And I took like, I took a long time to implement that efficiently, and that was that. Okay. I hope I convinced everybody that efficiency is a concern of ours. So we're going to think of how to do this efficiently, right? So, I think everybody could implement like cheap abstractions that are inefficient, right? And now here's how we stitch the storage into the big string. We're going to simply have use private inheritance. I think some people can't see because of this, right? You didn't say a thing. Okay. So we are going to use private inheritance to inherit storage and have it as part of the string. What are the problems with that? Private inheritance. What are the problems with private inheritance? Derived classes could not hook into the implementation. For the record, is string intended to be derived from? Let me ask you again. std string, is it meant to be inherited from? Who says yes? Cool. So you're mentioning like we could have a problem if we did, but we don't, right? Okay. Another problem with private inheritance? Yes?
Isn't inheritance like the strongest possible relationship you can have between two things?
It is, but I would say that storage is already as tied to the string as it gets, right? Okay, let me ask you something else. What are the problems with public inheritance?
Gives you access to storage.
Okay, hands up. Yes.
Full access to the storage object with no way for the flex string to control that access. And of course,
What is a very concrete, let me rephrase. What's a very simple and concrete problem with public inheritance like that? Yes. That happens in either case. Dependencies. No. What is a simple, let me ask again, what's a simple, obvious problem that we have? Somebody who hasn't answered has a hand in the back. Yes, sir.
Change your mind later about how you want to implement it. You don't have that flexibility.
Okay, that's a problem. It's not simple. Yeah, it's a problem. It's not simple. Yes.
The string is not a storage.
A string is not a storage, so we have an identity problem, right off the bat. A simple problem that I meant to mention was that if you have public inheritance here, people are going to be able to take a pointer to storage from a flex string, take a pointer to storage, hang out with it, and later delete it. Right? Call delete on it. Right? It's going to be code that compiles very nicely, flag free, right? And it's going to blow in your face. Right? It's just undefined. Okay. Now we're going to start cranking implementations of storages for strings. And we have a number of interesting stories. Okay, here's a simple storage. I have a pointer to data that has a pointer to the end of data, a pointer to the end of the buffer, and it's going to continue with the buffer. Question?
There was a problem with the private methods?
Thanks for asking. The problems that could appear with private inheritance are so unlikely to appear. It's about name collision that basically you can use it. Thanks for asking. Yeah. So I would endorse that. Yes.
Can you also explain what you said about deletion? If you have a
Oh.
structure, okay?
Yeah, thank you. With the virtual destructor, you're fine. But once the destructor is virtual, then you're going to start thinking about making a lot of other functions virtual, right? And here, this design is not intended to waste efficiency for the sake of allowing people to call delete whenever they want, right? Okay, thanks. All right. So let me draw on the whiteboard the structure here. Okay, that's interesting. We only have this whiteboard. We can't wipe it. I gotta be, we have a string object, and it has the pointer p data, right? P data goes here. Can everybody see? People in the back? I hope so. Oh, thank you. Thanks. Okay, what's the first member of data? So this is p data. What's the first member here? P end. Second? P end of mem. So this is P end. This is P end of mem. Okay, and here I have a buffer of size 1. Right? So I have this guy of size 1 here. Now, the thing is, I'm going to tell you an ugly C hack from your C days that you used and loved. If it's for me, I'm busy. Basically, that allows you to do this. I'm going to allocate this guy, and I'm going to allocate extra memory after this guy, after the struct. And basically, I'm going to be able to index further than the declared size of buffer. I'm going to be able to index, as long as I have memory. So buffer starts here, but if I allocated more memory, I'm going to be able to say, oh, buffer of 2, buffer of 3, and buffer 1, buffer of 2, etc., right? So that's the struct hack. As long as you allocate memory carefully, right? Just have to be careful with that. Okay, what are the advantages of this versus like a simpler design that doesn't do this trick? What are the advantages? You have a single allocation whenever. So instead of having like I have either I have 3 guys here and they point to different things. That would be a problem because the string is going to be bigger. Right, so an alternate design is this. The string has 3 pointers, and there's a buffer somewhere. Right? Problem. Size of an empty string is going to be larger. Right? 3 times. If you have a lot of empty strings, that might be a problem. Right? Other than that, there's no major problem. If I say, I'm going to allocate the pointer to 3 guys here, and then these guys are going to do whatever, I'm going to have the double allocation problem. Okay. Let me ask you this because I want to make sure I'm giving you value. Do you care about efficiency? Do you care about efficiency? Not compile time efficiency. I know you care about that. But efficiency, like in terms of execution speed? Size? Okay, what's more important, size or speed? Who's for speed? Who likes size? Okay, sound like both, huh? Okay. I take it like people who didn't raise their hand, just you know what, I'm fine. Okay. So that would be our first shot at an implementation. It has advantages and disadvantages. Now, let me tell you a little trick. An empty string, right? An empty string should have like, could p data be null for an empty string? Yeah or nay? So the pointer, so the string has 1 pointer to that thing, right? Could it be null for an empty string? Yes, but you'd have to test for it everywhere, right? So that's inefficiency. What other design would you think of? Huh? Yeah. So yeah. Did you read? No. Okay. So what I've done in the implementation was something a very simple trick. I allocated a very small 3 pointers with just 1, 1, 0 and an empty string, and I have everybody point to it. So the empty strings are shared. Why could I do that? There is one thing about the empty string that makes it possible to do that. That's not true about any other string. Yes?
You're never going to write to?
Yes, thank you. So the empty string is by definition immutable. I mean, you can't modify it because it's empty, right? So that's the pager. You got to run, right? I'm touching a nerve here. So, okay, so the empty string has this particular quality. It's immutable. Nobody can change it in any way, and therefore it can be shared, right? Otherwise, you couldn't. Okay. Now, let's talk about other implementations. So as I said, each implementation of a storage is going to have its own, advantages and drawbacks. No one is going to be perfect. Some other simple implementation would be vector string storage, which simply takes an STD vector and uses it as a backend for a string. A vector is, after all, a buffer, so I could use it, right? No problem with that. Okay, that's a very small implementation because I'm using something already offering a lot of functionality right there. Other ideas would be segmented string storage. You have a huge string, and you're going to store it not as a contiguous chunk of memory. You're going to store it as several segments, right? You could have DBCS if you still care about DBCS. So now, I hope this convinces you that we have a lot of flexibility going on here, and it's not very hard to plug in more flexibility. And I would like to give you some statistics for what we have so far. Believe me, we haven't gotten to the fun part yet, which makes me nervous because like 5 to 2 already. So the shell, what was the shell? The shell was the collection of nice to have functions implemented on top of storage. Right? Are you with me? So the shell is like all the cute functions, right? 780 lines. That's going to stay constant. And then we have 170 lines for the simple string storage, which we discussed. We have 160 lines for a string that uses its allocator. There's only 75 lines for a vector string storage. And all of a sudden, if you do the math, we got 3 distinct implementations featuring different storage models and different trade-offs, right? With a total of 1,185 lines. And if you divide that by 3, we got only under 400 lines per string implementation, right? And that's that's 3 fully functional strings in one shot, which is very nice because a pretty industrial strength implementation is going to be over 1,000 lines. So that's pretty cool. But I'm trying to think which is the interesting slide that I need to wake you up. It's the next one. Let's think of this. Let's think of how can we factor the small string optimization into this design. What is the small string optimization? The small string optimization is, anybody knows? Is the following. If I have a string that has, okay, let's say it doesn't have only a pointer. Let's say it has like a pointer and some extra data. Say we go for the 3 pointers. What's the size of this on a 32-bit machine? 4 times 3, that's 12 bytes, right? Okay. Now here's the small string optimization. We have 12 bytes hanging out in there, right? And what if I have to store a string that's like 5 characters? Like a mutual fund, right? I'm going to start thinking, why would I allocate, like, I have these 12 bytes already. I'm going to allocate some pointers and do all this stuff here just to store some 5 little bytes here, and I have a huge overhead per, per character, right? Let's think of this. Let's do the following thing. We're going to say this. We're going to have not 12. So you're going to have like 13. The last character here would be a Boolean. The Boolean says, this is a small string or this is a big string. Okay? Now, if the Boolean says it's a small string, then the characters are going to be in here. Neat, right? No allocation. The characters sit in lieu of the pointers. They sit where the pointers are. They are in the pointers. They occupy the same storage, right? That's pretty cool. I like it. Once I'm trying to grow the string to the point where it can't accommodate the small string anymore, we're going to flip this Boolean. We're going to say it's a big string. We're going to do all the allocation brouhaha. Okay? That's pretty neat. And again, this I think of what a nice design this is. And it's pretty nice. It offers you, it's transparent. You don't know. For you, it's all strings. Small, large, they take care of themselves. And it works very well with short strings, and it still works pretty well with long strings as it used to work, right? And this is exactly what I have here. Questions about this design? Yes?
So is small, actually is large if you're using it as the zero terminator and the discriminant?
That's a very good question. Thank you. You kind of stole my thunder because I plan to kind of nicely prepare for that and then say, you know what, I'm going to use that byte for 2 things at the same time. So that's a very good remark. Have you been in this talk?
Yeah, but you have the point there.
Okay. Yes.
Is the checking of that Boolean going to cost you time?
Yes. Thank you. Yes, thanks. That's a very good point. As I said, no design is perfect. Or if I haven't said, I'm saying it now. No design is perfect, right? It has trade-offs. I mean, it's by necessity, you're going to have some, there's no free lunch, right? So yes, that checking of the Boolean is going to cost you some time for the space that you're gaining. Yes? Would it make any sense to put the Boolean inside the union? One thing you don't, I think you wouldn't want is that the Boolean, some pointer is going to step onto the Boolean and write some random bits to it. So we're going to go very low level here, by the way. We're going to do some low level stuff, which is fine. It's like playing the mud. I like it. Okay, so here's how it works. I have a union, I have the small string, and I have the big string, and that's it. And I have the Boolean. That's it. Let's see how we go about this in a little more detail. Okay, this is the interesting slide. So please wake up, pay me some attention here, and then you can do whatever. So I'm going to do something very audacious here. I'm going to say this. Okay, I have the small string optimization. I'm writing it as a little class with that union, the Boolean, all the good things. Good. But this little optimization class is taking storage as a template argument. And here's what we're going to do. That's the fun part. We're going to be able to graft the small string optimization over any large string that's out there. We're going to be able to graft the small string optimization over any other string. And this means I can have reference counted and a string with the small string optimization. I could have whatever reference not counted string with the small string optimization. I could have multi-threaded string with a small string optimization, and so on. All of a sudden, by writing this one class, and this is the important point, by writing this one little class, I not only added one class to my system, I doubled the number of things that I have. Does that make sense? This is very important. So, yes?
You have a lot of legacy code that handles, takes standard scripts, right? What's the compatibility here? It uses a different class.
Thanks for the question. So, okay, fundamentally, like consultants don't care about legacy code, right? So, if you have a lot of legacy code, please understand that this is all static. It must be compiled into your application, right? The underlying memory, memory model, we don't have one. It's fragile, right? So basically, what I'm saying is that if you change this, you got to recompile. Okay. The legacy code, as long as it doesn't do any mem copy over the strings or anything, it's going to continue to function because you're offering the same interface. But the underlying binary model is not going to be the same. Good question. Thank you. Okay. And here's an example. Here I'm type defing a flex string that uses characters, is the standard, traits and everything. And it's going to use the following storage. I'm going to use the small string optimization for characters up to 19 characters over a vector, so this is for the large strings, over the vector string storage of car. Yes?
It would be possible to replace the 19 with, say, 1,000, which you could end up with this base thing instead of being 13 bytes, it'll be 1,000 bytes.
Yes, that's a very good question. So how about if I put 123 in there, right? What application domain would you think that would be very useful for this setup? Okay, if nobody answers this, I'm going to kill myself. What application domain is going to benefit a lot from efficient strings up to like 4K? And then it's going to, without buffer overruns, it's going to support more. Yes? Web servers, anyone? Right? I have an URL that by the standards got to be like 4K max, right? But of course, the bad people are going to try to push more. And for the good people, I'm going to have the small string, which is efficient. And for the bad people, I'm going to still not buffer overrun. I'm going to use a vector that's dynamically allocated. So thanks for the question. OK, so it makes a lot of sense to put a lot of interesting numbers here and see, for application domain. So that's flexibility right there. Now, very important. I have an advice for people who use templates, in whatever settings. Do use typedef. Typedef is a very good abstraction for templates. It's basically factoring all this complicated stuff, which is a design. So this is like this. I'm designing a string that does this and that and the other, right? This is a little design right here, and the typedef gives a name to the design. I'm going to say string. Whenever I want to use this design, I'm going to say string, right? The advantage is that whenever I want to change the design, I'm going to want to put other numbers here or other strategies, right? It's going to be different. Compare that to the idea of inlining this, behemoth declaration here wherever you want a string. It doesn't make sense, right? So do use typedef. I mean, it's just not typedef. It's a powerful abstraction device. Here's another idea for a web server. Say I combine the small string optimization with a string that basically rejects everything. It's like a string that doesn't accept any character in it. What am I going to obtain?
You'll be safe against.
I'll be safe because of the tests. I'm going to have like this. It's a string that's maximum 8K. And beyond that, it's just going to throw exceptions, right? It's pretty cool. And I like this because it kind of gets something from nothing. Like I have this dummy storage that simply doesn't do anything. It just throws, exceptions wherever you try to store something in it. So that's a good thing. That's a cow, in case somebody doesn't see it. I hope the cow didn't copyright the image. Just pull it from the web. OK, so we mentioned the problem with cow, which was cow. The copy and write doesn't work well with threads. Yes. The hidden sharing. Yes. So fundamentally that's the problem. However, we are human. We do write applications that do not use threads. And even in applications that do use threads, we do have large portions of them that are not multi-threaded, right? So maybe we have an application in which the threading part is very confined, very little, and most of the application is going to be like, single-threaded. Because of that, cow can be very nice. The cow is a nice animal, except when it's mad, right? And there are many examples in which you have large strings that are just there for the entire application that are heavily shared. Example, language parsers, like you have the keywords and everything and the identifiers and all that. It's very nice to have them shared and not copy them all over the place, right? That's a good thing. All right. And now we're going to, this is another interesting slide, even bearing the cow. This is an interesting slide because it does the same trick once again. We're going to have the cow take a storage as an argument, and basically I'm going to build copy and write over any string. And again, I'm doubling my behaviors because I can plug any storage in here that we already have. And all of a sudden, I have double as many from the small string optimization, and I have double as many from the cow. That's pretty neat. I'm going to come with some statistics later. So here's how it works. Very simple. The cow is like a classic thing. It has a pointer to a data. That data contains the actual storage and the number of references. I'm sure everybody here has designed at one point or the other some reference counting scheme, right? So it's just the straight classic reference counting with the addendum, with the addendum that we have this storage here that's generic and could be replaced. So this class, this little class, is much more generic than run-of-the-mill copy and write. Okay? Questions? Okay, everybody knows the cow. Now, we have 250 lines for the small string. We have 400 lines for the cow. Because just, it's just clunky, it's just straight code, but you have to write it 400 lines. Now, the small string can be combined with a cow, right? So if I have a small string, at best it's going to be optimized and stored right in the string. But if I have a big string, the better it's shared, right? So all of a sudden I have two advantages I'm aiming for, right? Not only one. Now we have 24 possible combinations, but only 12 make business sense. What combination between the reference counting and small string do not make sense? That's a good one. So which combination between reference counting, copy and write, and small string optimization do not make sense? Okay, let me put it another way. If you had a very short string that takes a nanosecond to copy, would you share it? Would you pay additional overhead for the sake of sharing it because you thought it's too long? Okay, let me ask you another way. So it's, yes? The empty string, what about it? Yes, so that's a very nice limit. So we have one point here that says, the empty string, you don't want to reference count because it's empty, right? Let me ask you this. One string of one character, do you want to share? Do you want to pay money to share that? Yes. Awesome, thank you. That's what I was looking for. You know what? You're going to get the book. Thank you. So come after this and I'll give you the book. I can sign it for you if you want. It's not very nice, but it's okay. So yeah, I do not want, reference counting is all about long strings, ladies and gentlemen, that I do not want to copy around. I want just to share. Now, short strings, I don't care. So the combination that would end up reference counting the small strings, I don't care. That reduces the useful combinations in half. So I had 24 possible in the world combinations, but now I'm going to stay with 12, which is still pretty good because we have 12 behaviors in 1,800 lines of code. And if you do the math, it's going to be some periodical thing here, which is like 150 lines per string implementation. That's the idea. It's less code, more software. It's to me, it's a very cool thing. It's almost like magic because you got the more you write code, you multiply the outcome of that code instead of just adding the code. Before going to conclusions, let me show you that trick with the zero terminator. We have still 5 minutes to go. Questions if you have right now?
Someone who answered the question rather than someone who asked it.
That's a good question. You should get another book. But I'm sorry, it's given already. Maybe next time. Okay. By the way, you work for Amazon, right? There's a bad review for my book. That there's 1 in 50, but it's still a bad review. You know how it's like? I remember at the conference, I was like, going through 150 reviews after my talk, and I flipped through, and they say it's cool. I like it and all. There's one guy who said, Andrei really is, it's terrible, and stuff like that. That one guy, I lost my sleep over. How could that guy think, that bad of me? So that's what happens. We ignore the good. We only look at the bad. So back to the good. We have a buffer here for a small string optimization. Let's say it's like 1, 2, 3, 4, 5, 6. So we have like up to 6 characters we're going to store small strings. And here we're going to store 5 minus length. I just have this convention. I'm going to store 5 minus the actual length of the string. So when the string is empty, here there's going to be the number 5, right? When it's like 1, this is going to be 4, right? I can very easily return the length. I just say 5 minus whatever, and I'm going to obtain the length, no problem. Now, okay, so I store A, B, C, D, E, F. Okay, here an adjustment would be necessary. By the laughter, I guess not only I made a fool of myself, but you all understood what I was aiming for, right? So what's going to happen is that as I reach here, like the 6 characters limit, this guy is going to be 0, and very nicely is going to serve both as the encoded length and the 0 terminator for the small string. So that's pretty nice. I mean, we programmers like this thing that, come on, it's 1 byte. I mean, who cares? The grand scheme of things, but everybody likes it.
Are zero terminators really relevant?
Oh yeah, that's a good question. How about the terminator? Because it's string, it has the length, right? But, yes, 1990s? 90, what about them? Yes, that's true. You should allow, and string does. And this we talked about does. But, huh? Yeah, I mean, you can have, like, if it's AB, you could have a 0 here and you're cool, right? And you store here like 4, right? That's fine. But why would you still care in like a string like the, rocket spaceship era string? Why would you care to store terminating 0, with every string? Why would you care? Yeah, I mean, inevitably you're going to printf to it or do something with it that's with a C-level function, and that C-level function is going to expect you to have an alternative string. Therefore, all the string implementations I know of, they always put that extra 0. Even if you have embedded nulls and everything, they still add that extra 0 at the end. Yes?
The standard mandate that CMS requests are
Louder?
Doesn't the mandate for the standard mandate that CMS requests are returning?
Yes. Yes. So there is one function, but you could take the address of the first character, right?
Right, but it still needs to return a 0 terminated string of characters.
No, if you take the address of the first character and do not use sister, if you don't use that guy, you're going to have trouble. So let's take this in the large. So there is a function, C_str, that basically says, whenever you call this guy, there's going to be an alternated string. It's going to give you an alternated string. But bad programmers take the address of the first character and stuff like that and still play with it, right? So for those guys, we always have the 0 there. We're contributing to yes. Yes.
You made one point earlier that ruling that says whether or not it's a small string optimization can also be fit into the same piece of memory as you were putting your pointers.
Okay, don't put words in my mouth. Someone else suggested that, and I said that's not possible because you don't want some pointer to trump over, right? However, there are ways, but you have to know the exact memory model of your computer. Like, for example, there are computers that do not allow you to allocate memory at odd addresses. There's 1 bit right there. We have 1 bit, right? And that bit could be the Boolean, right? Pretty neat. Neat in some wicked sense, but, neat. Okay. So the answer is yes, with, provided you know a lot about the architecture of the computer you work with. Any other questions? Yes?
All right, based on these policies, we can have 12 distinct types of string. That's really nifty.
Is there some way we can make it possible to use two different ones and assign from one to the other?
That's a very good question. Thank you. So the question was like, I have all these nice strings, and maybe different areas of my application are going to use different trade-offs. Like some guys use a small string, some other guys like the cow, and so on, right? Now, how do you think you would assign among such different strings? Okay, someone who knows std strings interface. How can I assign among any two different strings?
Take the integrator from the start to on and pretty much build the rest.
Yeah, thanks.
And it doesn't really matter what types they are, as long as the underlying character type is the same.
So basically, thank you. That's the right answer. String has a function called assign that takes any pair of iterators. It's a template. Takes any iterators. There could be begin, end, and assigns the string to the range. And that's going to, on a good implementation, is going to translate into a mem copy of one string to the other. So yes, you could assign with this particular function, which is supported by string. Thank you. Very good question. All right. Now, I'm going to hang out for only 5 more minutes. So let's conclude. I'm going to hang out here. If you have any questions, I'm going to take offline. So we talked today not only about using templates, as I had promised, like you have to talk on templates, but it was templates plus some other little things. And we talked about how with policies you can just write some linear amount of code and achieve exponential return on investment, right? That's pretty cool. It's like investing. So policy-based design is very good when you need rich behavior. You want to tweak behavior and you want to switch from one string to the other and stuff like that. You want policy-based design when you need flexibility, and that's compile time flexibility, right? Not runtime, because we'd be doing virtuos otherwise. Very nice point here is that the abstraction is non-cost. The performance of flex string, if you're gonna measure it, is just as good within percents of any monolithic string implementation of the same design. Everything is going on at compile time, and the compiler is going to be able to optimize everything. Okay, so that's a very important point. It's a non-cost abstraction, and it's flexible because later you come with your own idea of a string, and you can very easily write it and plug it in. Any other questions? Yes.
So is there any way to enforce logic policies, like enforce the global reference count small strings?
I'm not sure I understand the question.
So, it doesn't make sense to reference count small strings, right?
Yes.
Is there any way to enforce that?
Oh, to enforce that. Yeah, that's a good question. There are ways. I believe you're not going to get a lot from that, because basically the guy who combines the policy is going to be a designer. You're not going to give that to a junior program, right? There's going to be a designer who's going to put the right type def in place, right? And that guy is going to think through and figure out what, it's a design thing, and designers are supposed to do a good thing. Yes?
Talk about components that accept and expose the same interface can be powerful.
Yes.
If you have multiple components that behave like that, it seems like you get into trouble that, like, if you sequence them in the wrong order, they have worse behavior than, like, there's a right way to sequence them and a wrong way or a less ideal way, and is there any way that you can express that so that when you try and compose your ideal string, you don't get the order wrong?
That's another facet of that very question. The same very question. Like, how can you prevent bad people from instantiating the policy in the wrong order and not knowing what they're doing, right? But again, given that those are not the programs are going to use it. The designers are going to be the people who put the type def in a header file, right?
But so his question was related
to how you enforce.
C, as opposed to the internal performance.
Yeah, I don't have a good answer. I mean, at best, you have to measure, because you can't know in advance exactly which works best for you. Yes?
At least this way, you gain on the action control. It's really easy to just swap them, to try everything without having to crash the rest of your code.
I would say with Perl it's a bit easier than with like 1 million lines of code C++ application, but yeah, that's a good point nonetheless. Yes.
Time it gives you a lot of that power.
Yes. Yeah.
Time.
Yeah. Thanks. Okay. Last question. Yes.
Kind of a general STL question and answer, statement string question. What would you recommend as a solution to the problem of when someone passes a null pointer to a function that's expecting the STL string as a parameter in the default constructor for that creates an empty statement string or causes a segfault that seems happening?
So the question was, what do you do when people pass in the null pointer when they're not supposed to? Okay, here's my advice. If it's a static function of limited visibility or a private function, you can assert. If it's a public function or a high visibility function that people, the litmus test is the following. If anybody can link into your function and call it, then don't do assert. Do a full-fledged check and just throw something, return an error code. Do proper error checking. I'm saying this because of the following. In a large application, such little things like expectations don't work very well because it's a large team, programs don't know very well what's going on and stuff like that, right? So if it's a static function of limited visibility, you do one thing. If it's a function that everybody can link to and call, you do the other thing, full-fledged checking, right? With this, I'm going to conclude. Thank you very much.